Welcome back to Solid Simulate. Today we are going to simulate an airfoil in ANSYS Fluent. This project is about validating NACA 12's results. The process of creating an airfoil in SolidWorks was already covered in the CFD tutorial, but today we are going to take a closer look at how to build the proper two-dimensional model for Fluent. To have better control over the mesh, we've created several nested domains around the airfoil. And an important note, when creating this nested surface in SolidWorks, the outlet boundary of each domain becomes the inner boundary of the next one in the following sketch. To make sure Fluent recognizes the simulate surface, we use the planar surface command in SolidWorks. For example, you can use this command to generate the surface from the first airfoil sketch. And that's how we create the next domain and sketch step by step. The step is to move into Design Modeler inside ANSYS Fluent. Here, all we need to do is import the geometry we've just created. The first step is creating proper mesh is define the boundary condition. These include the airfoil surface, the inlet domain, and the outlet domain. For better control and mesh density, we refine the airfoil edge using edge sizing. Then we apply face sizing to the nested domains to get a smooth transition between regions. Finally, to capture the wall effects and control the Y plus value, we create inflation layers with an appreciate first layer height. This ensures accurate results near the airfoil surface and improves the overall solution quality. As you can see, the mesh has been generated with the good density and proper boundary layers. Now, let's check the skewness. Ensure the mesh quality is acceptable. Ideally, the skewness should be below 8500 for stable and accurate simulations. Clicking Setup, we enter ANSYS Fluent and start defining the solver settings. We'll use a pressure-based solver with steady formulation and keep energy turned on. For the fluid materials, we set air as the working fluid. Under operation conditions, set the reference pressure to 1 atmosphere. According to the reference paper, the inlet velocity is 17 meters per second at 0 angle of angle. For the outlet boundary, we use pressure outlet condition based on the static pressure. Solution method, we use a simple algorithm with a second order chain for better accuracy. As described in the guide file, convergence criteria for the airfoil are set to residual target of 1-6 and lift coefficient. For initialization, we use the standard initialization method, taking the inlet as a reference. After that, we set the number of iterations and start the calculation to reach convergence. Please ensure that the solution is stable and fully converged before extracting result. Next, By using contours, we can analyze the velocity and pressure fields around the airfoil. Here, you can see that the solution has converged properly and the flow looks consistent. From the report section, we can extract the lift and lift coefficient values for validation. We repeat the same simulation step for other angles of attack, such as 5 and 10 degrees. Please save the current workbench project, reset the solution, and modify the setup in Fluent. By comparing our numerical results with experimental data from the NACA reference paper for NACA 0012, we can confirm the accuracy of our simulation. Next video, we'll go deeper into flow suppression and visualize the vortex formation around the airfoil, available in the full course.